Graphing quadratics in the vertex form worked out nicely because we were able to use the concepts of key points and transformations to understand the shape and location of each graph. However, we're often given functions in the standard form, and converting these to the vertex form each time could get tiresome. Plus, there are still plenty of lessons we could learn from the process of graphing the standard form. The big question then is, what strategy should we use for graphing the standard form? Well, to start off, we'll simply choose some inputs that are easy to evaluate and keep doing so until we can see the general shape of the graph. This will allow us to observe some additional features of these graphs and develop more refined strategies from there. So let's get to it by graphing the standard form. Let's jump into it by graphing this function. We'll make it easier to show our work by making an extended table of values. And in that extended table, we'll have 5 columns. The first column will be for our input, but then the next 3 columns will be for the individual terms of the function. Then, our final column will be for the output, which will just be the sum of the 3 middle columns. Once we have that made, we'll have to decide what numbers to choose as our inputs, and we'll start that process by choosing some numbers that are easy to evaluate. Many people's first choice here is 1, and that will indeed be pretty simple to evaluate. And once we get our output, we'll go ahead and plot the corresponding point. However, there is an even simpler input to choose. If we pick 0 as our input, then the first 2 terms of the function are simply 0. This means that the constant term of our function ends up as the output of the function as well, and when we plot this point, it ends up being on the y-axis. We call this point the y-intercept, or the vertical intercept, and this point ends up being a great place to start when graphing the standard form. Now, before we move on, we should ask ourselves, how do we find the vertical intercept in general? Well, if we look at other points on the y-axis, we'll notice that they all have an x-coordinate of 0. In fact, another way of expressing the concept of the y-axis would be as the line where x is equal to 0. This means that if we want to find the vertical intercept, we just need to find a point on the graph where x is equal to 0, which is easy enough since x is the input. We can simply plug in 0 for x, and we'll get the output for our vertical intercept. Thus, in our general case, the vertical intercept is at the point 0, c. From there, we'll go back to the specific problem at hand and attempt to determine more about the shape of the graph. We know from our experience with the vertex form that graphs of quadratic functions are parabolas. However, there are 2 broad situations here that could be occurring. Most parabolas that we've encountered so far open upward like this. These parabolas start with a decreasing interval and then switch to an increasing interval after the vertex. And since the value of our function decreases as we go from 0 to 1, that could fit this situation with a graph that looks something like this. There is another possibility though. Some parabolas open downward, like this, and in this case, the parabola starts with an increasing section and then switches to a decreasing section. A downward opening parabola could fit our situation with a graph that looks like this. So, which situation is it going to be? Well, if we try plugging in a couple negative numbers and plotting those points, we don't get any indication of being closer to the vertex. So let's try plugging in a couple positive numbers like 2 and 3. When we get our outputs for those inputs and plot the resulting points, we can see that the function reached a minimum value at 2 since the graph goes up in either direction from there. This means that 2, -7 is the vertex of the graph, and that we can finish off by plotting a couple more points with inputs beyond 3 and drawing a parabola to match these points. This parabola clearly opens upward, and we essentially determined that by plotting points until we could see the general shape. Although there are many aspects of this graph that we could continue to discuss, let's move on to our next example to implement what we've learned so far and gather more information. Our next function won't be too different, but we do have to be mindful of the quadratic term since we're negating that term after we square the input. This, of course, doesn't affect the vertical intercept at all, but it will be important for any input other than 0. We'll be able to see that when we plug in 1, and we end up getting these two starting points that just so happen to be the exact same points we started with in our last graph. Then, we'll try to determine which way the parabola opens by extending our inputs a bit in both directions. In the rightward direction, we end up getting more points that decrease, but in the leftward direction, we reach a maximum value at -1 before the values start decreasing again as we move further to the left. This, of course, is actually an increasing portion of the graph as we move from left to right, which matches the situation we described earlier about a parabola that opens downward. So, what caused our previous graph to open upward, whereas this graph opened downward? Well, you might already know the answer, or at least have some suspicions. And if that answer was related to the value of a, you're probably correct. It turns out that if a is greater than 0, then the parabola opens upward. But if a is less than 0, the parabola opens downward. In this case, a is -1, which is less than 0, and so the graph opens downward. In general, this feature of quadratic graphs can help us determine helpful inputs once we plot our first couple of points. There is one other aspect of how we graphed this function that we should address now. After we plotted the point at -2, -3, we continued plotting points on the left side of the vertex without actually plugging in any inputs. So, how are we able to do that? Well, it comes down to symmetry. If we consider the input value for the vertex and move a certain distance in both directions, we'll get the same output. For example, we can see that -2 and 0 both had outputs of -3. This also means that -3 and 1 should also both have the same output. And since we already knew that plugging in 1 gave us an output of -6, this allowed us to also use -6 as the output for -3. This symmetry can be formalized a bit more by drawing a vertical line that goes through the vertex of the parabola. By doing this, we can see that if every point of the parabola was reflected across this line, we would get the exact same parabola. Because of this, we say that the parabola is reflection symmetric, and we call this midline the axis of symmetry. In this case, the axis of symmetry can be expressed as the line x equals -1, since every point on this line has an x-coordinate of -1. In general, however, the equation for the axis of symmetry isn't very intuitive. The easiest way to determine the axis of symmetry is probably to convert this general quadratic expression into the vertex form, and then use the value of h from that form. This might sound like more work than it's worth, except that we essentially already did this process when we derived the quadratic formula. It turns out that if we split the formula into two separate fractions and ignore everything from the plus or minus sign onwards, we end up getting an equation for the axis of symmetry. So let's jot that equation down in our feature summary and move along to our next problem. For our final problem of this section, let's look at a function that has a more noticeable value for a, -2 in this case. We'll once again make our extended table of values and start by plugging in 0 and 1. Then, with the knowledge that the graph opens downward and the location of our first 2 points, we can determine that we should primarily plug in numbers that are greater than 1. With these additional points, we can eventually get a rough idea of what the graph will look like, but you may notice that our symmetry seems to be off. Thankfully, this lack of symmetry is just a side effect of having -2 as our leading coefficient. If we plugged in some fractions, we would eventually see that all the points still come in reflective pairs. Those pairs just happen to involve some non-integer inputs. From here, we could fit a parabola to these points as best we can and move along. However, this graph might be better suited to a different graphing strategy. Given what we just learned about the axis of symmetry, we have a new tool to utilize. We can start by calculating the axis of symmetry, which ends up being the line where x equals 7/4. Then, we can plug in 7/4 to see the value of the function at that input. This point is the vertex of the parabola, and since we also know that the parabola opens downward, we can then determine that this vertex point will be the maximum of all the outputs. From there, we can start plugging in other numbers, but each time we get a point, we can simply reflect that point across the axis of symmetry to get a corresponding point. This way, we can get 2 points on our graph with only one set of output calculations. Of course, it might be good to double check ourselves on some of these points, but eventually we'll see that this process is sound. And then, once we have enough points, we can finish the graph by drawing our parabola. While both strategies that we just utilized get us the correct graph, the second strategy may have a slight advantage over the first. Namely, that it finds the axis of symmetry first, which helps us explicitly find the vertex. Since the vertex of a parabola is arguably the most important point on the parabola, it's probably a better candidate to find first when compared with the vertical intercept. Because of this, let's even add the vertex point to our feature summary. The input coordinate of the vertex will be -b/2a, like we have in our equation for the axis of symmetry. Then, for the output coordinate, we could simply represent it this way. But if we want to get more explicit, we could actually evaluate that expression in the function to get this output expression. Thus, if we graph a quadratic function that's in the standard form, we get this vertex point, and these are the features of the graph that will be most important for our purposes. Given the features of quadratic graphs that we just established, let's make a few more graphs to continue practicing our skills. We'll start with this example that will help illustrate why it can be handy to use the strategy where we find the vertex first. When we plug 0 into our extended table to get our vertical intercept, we'll see that the intercept is nowhere close to fitting in our graphing area. We could, of course, keep plugging in numbers to see which direction we need to go to locate the vertex, but we might have to plug in a lot of numbers if the input coordinate of the vertex isn't close to 0. However, if we find the axis of symmetry, we can see right away that the input coordinate of the vertex will be 7. And if we plug 7 into our table, we'll get this output, which yields a point that fits on our graph nicely. Then, we'll note that since a is negative, this parabola will open downward. Next, we'll plug in a few additional inputs around 7, which will show us more of the parabola's final shape and allow us to graph the parabola. For our next example, we'll jump straight to finding the axis of symmetry and the vertex, which ends up having non-integer coordinates. However, Since the axis of symmetry is at the halfway point between two integers, we'll easily be able to utilize the symmetry of parabolas to plot extra points here. If we plug in -5, -4, and -3 as inputs, we'll get outputs that can also be utilized for -6, -7, and -8 respectively. We can even go one unit further out from the vertex and still get points that fit in our graphing area. And once we plot those points, we're ready to draw our parabola, which completes our graph. Finally, let's do an example with some fractional coefficients. While nothing about the process will technically be different, it will be a bit more challenging nonetheless as we do more complicated operations with fractions. In fact, this may be a good place to use some decimal approximations instead. So we'll simply use decimals and round each of our calculations to the nearest hundredth if necessary. Once we do our vertex calculations, though, you might notice a problem. The vertex isn't going to fit in our graphing area. In fact, if we graphed this example on the current set of axes, we would only end up with a small portion of a parabola in the corner of the graphing area. Since this doesn't tell us much about the parts of the parabola we care about, we'll remove these axes and draw new ones. Before we draw the new axes, however, let's find a few more points on our graph to get a better idea of what the ideal axes might be in this situation. We'll eventually see that it could work well to go from -5 to 15 on the input axis and from -20 to 0 on the output axis. This keeps the scale of our axes the same, which will allow us to compare the shape of this parabola with others that we've seen so far. Then, once we have those axes drawn, we can plot our points and draw our parabola to complete the problem. That concludes this video on graphing quadratic functions in the standard form. Hope you learned something new, and thanks for watching.